Okay. Good evening, everyone. So today we finish with transformers, and basically it will be a demonstration of a particular approach with the efficient transformers that we discussed last time. Efficient and transformers for time series. So let me share my screen. This one. Let's start with the data that we're going to be using. So it's a very nice data set. It's called electricity transformer temperature. So, and this temperature is a indicator of what is going to happen with the grid in the future. This data set is very special for the fact that it is extremely highly resolved in time. So this data set is available in several configurations. It is available in hourly configuration and also in minute configuration. So you basically have 2 years of per minute measurements of several transformer temperatures. So this data set is extremely hard for any other tool than a transformer, and on this data set, the time series transformers usually compare with each other. So each data point consists of 8 features, including the date, the predictive value oil temperature, and 6 different types of power load. It is available on GitHub. We can clone it, and it looks like this. So we have the date. Here you can see that we are taking the hourly data set because the minute data set is probably too much for this demonstration. And we're also, if we follow this link, let me follow this link. We will see that there is just ETT small. So they have ETT large and ETT full promised, but they have it promised since many years, so I'm not sure that it's happening. But we have these 2 electricity transformers at 2 stations, including load and oil temperature. All right, so we go into the ETT small, and here we have the hourly and the minute versions. We will choose the hourly, and you can see that the date increments by 1 hour. And this is the temperature. So let's look at this is the whole data. We have 17,420 hours, and we can calculate that it is going to be 725 days, which is 2 years exactly. Exactly 2 years of data hourly. And the last 700 points look like that. So you can see that the series is pretty intermittent as well. We can also see that there's a trend as well as there is some seasonality, and there is probably complex seasonality. So it's a really, really complicated time series from the time series from statistical point of view. Then let's discuss again the transformers a little bit. So let's remember the classical transformer, the vanilla so-called transformer. It consists of an encoder and a decoder. And the most important here is the attention block, which we discussed 2 webinars ago in great detail. Basically, it consists of several matrix multiplications, and we have understood that it is crucial for keeping the long-term dependencies because every token, we call it a token, is connected to every token, every other token through this attention mechanism. So when making a prediction, the model is capable of having everything at hand. In its limits, of course, because the context is limited by the memory. This we have already discussed. This is the drawback of the transformer is its computational complexity, which is L squared multiplied by D, where L is the sequence length and D is the hidden dimension, which is usually much, much smaller than the sequence length. And for forecasting, well, for long sequences in train or in forecast, it is impractical, so we cannot fit it all into memory. So we can say that vanilla transformer is memory inefficient, or compute. It's the same thing. So in this case, it's both the memory and compute bottleneck. So in order to process longer sequences, we need to do something with this quadratic term here. And for this, several efficient architectures have been proposed. So several approaches that improve upon the vanilla transformer are listed here. It is informer, autoformer, and FED former, head former, I will call it. And the way they improve is, so the informer model, first of all, it introduces a so-called probe sparse attention, which we will discuss later. So it's a modification of the attention procedure, which is essentially not computing full attention, and every not computing the full attention. So we will not be computing all of the attention. And second, it between the several stacked blocks of the encoder and of the decoder, it makes a shrinking of the hidden dimension to reduce also the memory pressure. So this is done to reduce memory use. Then it's all concatenated and processed into the decoder, which has which does not have here this problem. So what is this probe sparse attention? I have here a visual. So basically what we do is this is all our metrics queries by keys. What we will do is we will sample only a few of the keys chosen randomly. So then we will, so it will be much smaller than the total number of keys that we have, so much smaller than the sequence length. And then we will look at the dot product. Sorry, not at the dot product, but we will look at the KL. Yes, we will look at the dot product between each query that we have and these sampled keys. And we will look at the distribution of the dot product values between the different queries with the same keys that we sampled. So basically what we do is we reduce this dimension a lot. So this we do not use. Of course, it is sampled randomly, but we can think of it like this. And then we obtain such a matrix, rectangular, and we are going to, for every row of this matrix, we're going to compute the KL divergence. so the measure of similarity between distributions with uniform distribution. So we have these scores that we have here, and we will compare them with a uniform distribution. And we will say, if the distribution is close to uniform, then it is a bad query. It is not active. We do not need it in the current round of computing attention. So we will just simply ignore the lazy queries. We will only keep the active queries, which have non-trivial KL divergence with the uniform distribution. So this creates some kind of filtering for the queries now. Now what we will do is we will take this smaller amount of queries and use all the keys now. So we will now have a different matrix with reduced number of rows. And this is what we are going to be using further. So this improves the this improves the complexity of the computational complexity of the attention operation to log L, where L is the sequence length. Yes, because we keep the number of active queries proportional to the logarithm. So this is intentional. In practice, this is how we find the measurement of the KL divergence. So the good thing about KL divergence is that we can compute it in closed form in different cases. In this case, we can make an approximation so that we compute it in a closed form. This is the relation that we are going to use to filter the queries. And then the so-called distilling, yes, the reducing of the hidden dimension is performed using a convolution, then nonlinearity, ELU, and then max pooling for actual reduction. So the xn is the output of the nth attention block, and the n+1, sorry, encoder block, and the n+1 is the input to the next to the next encoder block. So we again reduce the memory usage to a logarithm, and this was the point of the Informer paper. And the reason for these improvements is in order to support longer sequences. Okay, so this was Informer. Autoformer is also bringing two benefits to the traditional transformer. So the first is the decomposition block, and the second is autocorrelation used as attention weights. So let's discuss this. So the decomposition block is basically decomposing the series X into X trend and X seasonal. How it's done is using smoothing. So we take our original time series and apply average pooling, which is equivalent to moving average filter for the series. So we obtain a smoothed series, which we can say is a trend. And in order to obtain the seasonality, we just subtract the trend part from the series part. This is only an approximation, of course, but this proves very handy. So it is handy to let transformers process the trend and the seasonal components independently. And most importantly, it is important to assemble the output from the predicted trend and predicted seasonal components separately. So I think that predicting trend is an easier task than predicting trend and seasonality at the same time, basically the time series itself. So we can get very good in the mean. Yes, and then, yeah. And the second thing is the autocorrelation used as attention. So how it works is that according to a theorem that we discussed in the lecture about spectral analysis, spectral theory of time series, there is a connection between covariance function, autocovariance function, and fast Fourier transform. So we can write an autocovariance function using the Fourier transform. This is exactly what is happening here. So the good thing about Fourier transform, and in particular the discrete version, the fast Fourier transform, is that it is in fact a differentiable operation that is implemented in, for example, in PyTorch, meaning that you can add Fourier transform as a layer into your neural network and backpropagate through it, which is very nice. So yeah, and you can optimize parameters. And this is how we basically quickly and efficiently obtain autocorrelations, right? Do I have the picture? So I have kind of this picture here. So what we need to do is the goal of all this is to look at the times, not at the whole series like this here, but only at the certain parts of the series which are sensible from a statistical point of view. And from statistical point of view, it makes sense to step back certain periods before. So for that, we will basically roll the time series. We will shift the time series and compute the autocorrelation using FFT between this time series and so I will denote it like that, and the same time series but shifted to one period. Yes, so we will if this was sitting here, it is now sitting here, but we will be computing cross correlation between these two. Yes, so between this and this, then between this and this. So using FFT, we will be computing this. And essentially, we're saying that these autocorrelations that we will compute, they form a vector, basically. Yes. So how many steps back we did? Then we will take only the top of these correlations, and we will reweigh them using a softmax function. So we will transform these autocorrelations relative to each other into a distribution. And why we need to do that? Because this is actually what we do in attention. So attention is a outputs a distribution to us. And then we will use these weights, this distribution, as weights in the parts of the rolled time series. Yes, so we will take, maybe it's a good idea to show this here. So I will take this, and I will compute R1. I will take this and compute R2, and then R3, and let's say R4, and I won't write anymore. Yeah. So then I will pick only top three. Top three. So let's say that R2 is not very good. So I obtain R1, R3, R4. Then I pass it to softmax to obtain a distribution. So I pass it to softmax. Softmax, and I will now call it alpha 1, alpha 2, sorry, alpha 3, alpha 4. And then I'm saying that the red thing here, this, is going to be alpha 1 times, I will call this S1, I will call this S2, so S for series, S3 and S4. So alpha 1 S1 plus alpha 3 S3 plus alpha 4 S4. So this is how it works. Basically, with the attention, it would be very much different. We would still be computing a sum, but we would not be computing the sum over the sensible places, over these S's, but instead we would be computing the sum over all time series, which can have zero meaning from the statistical point of view. Okay. So this is exactly what is written here, basically. And then there is one model that we did not discuss. It's called a FET former. FET for the frequency enhanced decomposition. So frequency enhanced decomposition transformer, or FET former. So the idea is also to incorporate the seasonality trend decomposition and also incorporate Fourier analysis. So how it's done is the following. There are Fourier enhanced blocks, and there is also a selecting of the Fourier components, which gives us linear computational complexity and memory cost. Again, this is for so this is completely for this for the efficiency, but the Fourier blocks are a little bit of interest. So the Fourier enhanced block basically resembles what we had already. So our original series is transformed into queries, and then we lift it to the Fourier space, to the frequency space. Then we do the sampling in order to achieve linear complexity. So regardless of the number of queries, we will do the random sampling. And we do the operations in the frequency space, and then do the inverse transform to obtain the output. And this is the block that will work on the queries, on the keys, and on the values. So this all happens here. And after that, we just do the regular attention, but in the Fourier space as well. So so everything resembles the classic attention, except the fact that we do it in the Fourier space, in the frequency space. This is how it looks on the graph, but really there is nothing more than doing it on the in the Fourier space. I think my runtime got disconnected, so I would need to rerun. Okay, so this paper has openly available source code for the FIT format, FET format. This from my CML 2022. And we are going to use this code to discuss several ideas. So I'm not going to go into every detail of how it works, especially model-wise. Everything is available on GitHub. If you want to have a look, I'm going to like more present you how we work with the data, because actually this is the most important part, how you process the data. So our data set, if you remember, looked like that. So this is a table in which we have the date, we have some features, and we have the target series. So we need to fit this data into the transformer. For this, we would need three definitions. We would need the sequence length, the label length, and the prediction length. So let me explain what it's going to be. So we have the X and the Y. This is the input. Input. This is output. Output. Okay. So X would consist of exactly sequence length items. Sequence length. This is just a part of our time series. The Y is a little bit more interesting. So the Y consists of two parts. So the first part is the label length. Label length. And then we have the prediction length. The length. So the label length is something that you can view analogous of the how is it called? Warm-up, of a warm-up time. So or a prompt, yeah. So we can say that this is a prompt. So this is available, and this is actually a part of the sequence length. So we take part of the sequence length, we put it into the prompt in the label length, and then we need to forecast what is going to be after. So this is unknown, and this is known. So this is how people do time series forecasting in with transformers, especially with transformers, because they do need this kind of prompt. Yeah. There are alternatives, so you can work differently with them, but because this architecture comes from the natural language processing, for them this is natural, and we just had to take over what is being used there. So these are the three sizes. Then there is the less important part. Yeah, so this code has the option to do the scaling. also different choice of features, and encoding of the time we can do. And essentially we obtain three so-called datas, three series. So the first series is the X, the second series is the Y, and you can see that they are identical in this data set. But this is not necessarily the case always. I will show you why they, so what is going on further, and you will see that this is not a limitation. And then the stamp is the date, basically data. So in our case, this is 4 features that are engineered from the datetime originally. So what happens when we do the get item is we will output 4 sequences. So the first sequence will be the input, the second will be the output, the third will be the time features for the input, and the fourth will be the time features for the output. So what's going to and the sequence X and the sequence Y is exactly what I just showed you. But this is all happening with these bounds called as begin, as end, R begin, R end. So as begin and as end. So as begin is the index where we are located. As end is the sequence length later than the beginning. So as begin to as end is simply the X. What is R begin, R end is going to be the Y. So R begin is the label length before the S end. Also, as I showed you. I will maybe draw it again. This is sequence line. This is our X. And then this is the Y. It consists of the label length, label, and the prediction length. So nothing too involved here. This is exactly what is written here. Label plus predicted. We could also write here as, and that would be the same. Right. So this is basically what data we are going to be getting at every index from our data set. So then after the data set is defined, we need to define the data loader. So the data loader is provided to us by PyTorch, so there's no need to define it. We just don't shuffle in the test, because we would want to assemble then the predictions into a single series, and shuffling would make things a little bit complicated with this. Otherwise, yes. So this is our data set. Let's run this. It disconnected again. Okay. Collab is very unreliable. I remember it. Yeah, disconnected again. Okay. I will make an attempt later because we need to also discuss a bit further. So let's discuss this code. So this is basically a runner. Yeah, so it has a function called train, and you just need to run this function, and it's going to train. Yeah, this implements the train loop. So I want to show you here that the model will be taking more or less our outputs from the data set. So it's going to be taking the X time features. Then it's going to be taking decoder input and the output of, and the time features of the decoder of the Y. And then we just need to compare the outputs with the Y and make a step of optimization. So there is not really anything happening here except for this decoder input. So the decoder input is assembled from label n of Ys. As I said, this is like a prompt, and then the prediction length is taken as zeros. So we just pass the zeros in this place. So that the Y is hidden from the model. It needs to fill in these zeros. The rest is dedicated to the model. And I have yeah, there is a little bit of initializations here. Let's try auto format, and let's try to run this after all. Restart session. Yes. Okay. On my computer, it's going to be much slower. Okay. Disconnected. Okay. I will try again. If it doesn't work this time, then I will maybe try on my computer. I just want to show you a couple of epochs to see that the loss is decreasing. So it works. And yes, so this is let me show you the parameters here that control. Yeah, this is the forecasting task. Yeah. If we would like to mimic the behavior that we were looking for in the homework number 2, we would put 1 here, and this is the sequence length. I think it was 20, and this I would put 10. So this would mimic the behavior that we were looking for in the homework number 2. But of course, this can be set arbitrarily, and it is actually better to set this to higher values because this is, after all, a transformer that can process longer sequences. So you can see, yes, iteration 1 finished, train loss decreased, well, from nothing, validation loss decreased. Then epoch 2, train loss again decreased, validation loss also decreased. So yeah, we can see that it is working as expected. Okay, so and then maybe let's have a look at the code for the models. So yes, in the models, you have the transformer, the informer, the autoformer, and the fed former. Let's start with the transformer. So here are our inputs. So the input sequence, the input dates, the decoder input, and the decoder dates. And we're going to just use the encoder and then use the decoder and output the result of the decoder. So let's see what is in this case the encoder. So encoder is a collection of attention layers, and the decoder is also a collection of attention layers, but made slightly differently, because the first layer in the decoder is the self-attention over the decoder inputs, and the second layer in the attention in the decoder is the cross attention between the inputs and the outputs. So let's see this full attention layer, and as you can see, the parameters in the decoder, where's the decoder? They are the same for these two attention layers, except for this first, which apparently controls the whether we need to use the sequential attention mask or not. So what this means is that I'm thinking whether we discussed it or not. Basically, in your attention matrix, you have access to all the elements, yes? And if our task, so this is the sequence, and this is the sequence, yeah? So both sides are the same. And then if we are asked to be forecasting this sequence, then sometimes what people do is they pass the sequence altogether into the decoder. So exactly like it is done here. Then it makes sense to prohibit the attention from looking at the future. So basically we split this matrix by its diagonal, and this is going to be set to 0. So this query is not allowed when we're looking to compute the attention here. We will not be allowed to look at these elements which are located in the future. We are only allowed to look at this element. And similarly here, we are only allowed to look here and not allowed to look in the future. So at the elements which are located in the future. So this is the mask, and this is how in practice the decoder is implemented. So essentially it is the same self-attention, but now we are using the mask to enable to disable the it from looking into the future of the sequence. Yeah, triangular causal mask, as you can see here. Yes. So this is the vanilla transformer. Let's look at the informer, for example. So the informer is comprised from the same thing, except for, so you can see it's very similar, but now instead of full attention, we have the prop attention. And also we have this convolutional layer, which is for the decreasing the size of the embedding between the rounds of encoding. Let's look at the prop attention. So what we do is we sample several keys. This is the number of them. And then we take the dot product between the Q matrix, the full matrix, and the small sampled matrix K. And then we apply this operation to compute the measurement of similarity between the profiles of every query and the uniform distribution. So this is already the closed form solution to that. There is no K divergence involved here. Then we take only the top queries. Then we only take these queries to combine it into the Q-reduce matrix, which is essentially just indexing the Q. And after that, we take the product, matrix product from the reduced queries matrix and the full keys matrix. And this is the output, essentially. So this is exactly how prop sparse attention is described in the paper. This this was not actually the forward method. So the forward method is here. Again, it accepts the queries, keys, values, and wait a second, it's because it's prop attention. Yes, of course, everything is fine. Yes. Yes, in the full attention, that was just simply the scores, the QK. Well, it's using the ANSOM, but so it's a little bit obfuscated, but the full attention is understandable to us, and this is even clearer, I would say. Let's go back and have a look at the autoformer. So the autoformer is using the autocorrelation layer instead of attention, but the otherwise the architecture is similar again to the transformer. So you can see that it's a decoder which is composed from repeated decoder layers, which are in turn composed from the attention-like layers. So there are two in the decoder and there is one in the encoder. So otherwise, encoder and decoder is very similar. Let's look at how autocorrelation is implemented. This is our forward. So we obtain the key queries, keys, and values. We take the fast Fourier transform or real value of the queries and of the keys. And then we take the normal pointwise multiplication between the queries and the keys conjugated, which is extension of transposition for the complex valued variables. And then the correlations is basically to take the inverse real valued fast Fourier transform from this product. This is the implementation of the theorem that we studied during the spectral analysis lecture. And then essentially what this does is it says time delay aggregations, which is essentially we need to roll the time series, and then we need to take the rolled time series with the weights described by the softmaxed version of the correlations. Let's look at how it is implemented, for example, in the inference. It is sped up, so we might not be able to really grasp what is going on here, but what is going on here? So the values, so the delays arc is pattern. So pattern is the so the pattern is the patch that we're going to apply, and it's going to be multiplied by the correlations. But as you see, we applied softmax to that, and the pattern is obtained using some torch magic. So I mean, this is gather. This is an aggregation function, and it is obtained from assembling this arrays essentially. So this is a little bit of high-level introduction into the transformers, efficient transformers for time series. I do not expect you to use this, and I would actually prefer you to use the straight vanilla transformer in your third home assignment. So just to remove all this clutter that there is here for your projects that you might be working on in the future in your studies or in your jobs. This is a very good base if you understand it well enough. So I mean, replacing the data here, so replacing the data set, you should be able to make it work with any kind of task, with any kind of data set that you have in your problem. I'm not sure that yeah, you can try to use this exact code for the third home assignment, which is I remind you to To improve on your result from the second home assignment. Друзья, а почему я говорю по-английски? Почему меня никто не прервал? У нас же курс на русском. О, Господи. Ну, как неудобно. Эм, Так, ладно. Эм, Тогда у нас, значит, еще упражнение в английском языке. Извините, пожалуйста, Да, надо... У нас курс на русском языке, и лекция получилась на английском. Да, класс. Давайте так, если у кого-то будут вопросы из тех, кто смотрит в записи, уважаемые слушатели, то, во-первых, вы сами виноваты, что вы не приходите. А во-вторых, пожалуйста, напишите, я постараюсь объяснить все, что непонятно. В общем, э, перехожу на русский. Да, Сара, тут повезло. На самом деле, я на ваше имя посмотрел и такой, ага, курс на английском. Поэтому, поэтому да. Ой. Я хотел сказать, что? Я хотел сказать следующее, что наше третье домашнее задание состоит в том, чтобы улучшить результат второго домашнего задания. Я вам его выдал уже неделю назад, но я сказал, что будет ноутбук, и ноутбук я пока не подготовил. Вот я подготовлю ноутбук, в котором будет так же, как для второго домашнего задания, выданы, условно, ячейки с кодом, и я подготовлю его так, чтобы там можно было, используя вот этот вот код, который здесь есть, сделать честное сравнение с тем, что у нас было в предыдущий раз получено. Вот. И после этого я вам выдам вот этот ноутбук вместе с ноутбуком с домашним заданием. Мне кажется, так будет разумно. И вы попробуйте разные модели. Я надеюсь, что вы также и посмотрите, как они устроены. Вот то, что мы сейчас смотрели, это очень важно. Эм, Ну, на самом деле там буквально переопределено вот то, что в формулах написано выше слайдов, да, вот это, вот это, и вот это, да. Тем не менее, это полезно всегда посмотреть для тех, кто хочет заниматься дип-лернингом или какими-то наукоемкими задачами с машинным обучением. Вот. На сегодня это все. Вы можете уже начинать работать над третьим домашним заданием, если хотите, самостоятельно, но можете дождаться и ноутбука, потому что с момента того, как я выдам ноутбук, пойдет отсчет 2 недели, и тогда будет прием третьего домашнего задания. Просто кто не смотрит семинары и не знает, что третье домашнее задание уже есть, у того будет 2 недели. А у всех остальных, кто ходит, у тех будет уже, получается, 3 недели, если с сейчасшнего момента смотреть. Нет, с того момента, как я первый раз об этом сказал. Вот. Есть ли какие-то вопросы по этой теме? Мне бы хотелось, чтобы с трансформерами для временных рядов мы на этом закончили. Дальше у нас будут специальные темы. Если вопросов нет, тогда я еще раз извиняюсь перед всеми слушателями за то, что получилось так, как получилось. У меня есть курсы на русском и на английском языке. И я сегодня решил их перепутать. Поэтому да. Если вопросы появятся после занятия, пожалуйста, пишите мне в личные сообщения, и мы постараемся все понять. На этом я тогда сегодня заканчиваю. Такое у нас получилось короткое занятие, и увидимся с вами через неделю. У нас будет занятие по теме ам, Change Point Detection. Это важная тема в классических, в разных прикладных задачах. Например, по-русски это называется предсказание разладки, да, то есть у вас есть какой-то прибор, который выдает какие-то измерения, и, например, температуру, да, и он может работать в двух режимах. Может работать в нормальном режиме, да, ну вот, не знаю, что у вас там, а, не знаю, посудомоечная машина, да, вот она, у нее нормальный температурный режим там такой-то. И сенсор показывает вот температуру, там она скачет, да, потому что у вас то холодная вода, то горячая, наверное, я точно не знаю. А потом у нее может быть аномальный режим работы, который означает, что она сломалась и работает на износ, вот-вот там вода польется, да, из этой посудомоечной машины. И вы знаете, вот ваши техники умеют это отлавливать с помощью температуры. Вот, значит, если температура там в определенном месте, она становится другой, тогда вы говорите, что у вас режим работы аномальный. Вопрос в том, как по стриму данных, да, вот у вас приходят в режиме онлайн данные о температуре. Как понять, что что-то сломалось, и выключить вашу посудомоечную машину, пока все не стало слишком плохо, да? Это задача предсказания разладки, и она возникает не только в посудомоечных машинах, а вообще говоря, много где. И даже в таких, казалось бы, далеких от временных рядов приложениях, как, например, видео, да. То есть вот у вас есть видеозапись, в которой, не знаю, человек играет эм, в теннис, да. Вот у вас есть, я не знаю, там минут 30 секунд видео, да, и у вас есть, допустим, два состояния, да, что человек ждет удар, да, и человек делает удар, да. И вот вам надо предсказать момент, в который, ну, вернее, на видео разметить тот момент, когда человек делает удар. Это тоже можно решать с помощью Change Point Detection, потому что у вас, получается, сменяется режим в данных, и тоже любопытно, как это можно делать, да. То есть вот мы можем это делать не только с непосредственно временными рядами, да, но и с видео. Я уже не говорю про звук. В звуке тоже, естественно, ну, звук — это просто как временной ряд. Эм, Поэтому да, задача важная, задача интересная, и о ней мы будем говорить в следующий раз. На сегодня на этом точно уже все. Спасибо всем, кто пришел.
Спасибо, до свидания.